Just ride with me, yeah. And I'll be here for you when there's no one else. I see things been getting hard, you need somebody help.
Hello and welcome to the video on limits and continuity in several variables. So if we recall, let's go back to the limit definition in one variable. So when we had one in one variable, that means that for the limit to exist, that requires f of x. So that required f of x to tend toward L, some limit L, right? So some value L as x approached, let's say some A, from the left and the right, from the left and the right. So it had to approach the same limit, right? So from the left and the right, so from both directions. Now that we're in multivariables, so two or more variables, then that requires kind of a lot more like complicated things, right? So in two variables, for example, like f of x, y, this must tend, or like approach or go toward, right? So tend to some limit L, okay? So same limit L, no matter how our xy point, how that approaches some point P. Approaches some point P, and P in this case is like our A. That's the point that we want to approach. Okay, so basically, like graphically, what this would look like is here's x, y, z. Okay, here's our surface. Let's say something like an umbrella sort of thing. Okay, so let's say this is the point that we're looking at, and on the xy plane, here's P. Okay. And when we approach P, from this way, from this way, from this way, it could be squiggly even. It doesn't even have to be a straight line. It could be any kind of curve. Any way you approach P on the graph, on the surface, it has to approach it that same limit right here. Okay? So, no matter how, in another sense, this doesn't mean like just from the left or just from the right or anything like that. This means from any direction. So I'll just write it over here. So from any direction or path, okay? Direction or path. This could be approaching it along a curve, approaching it along a line, anything like that. So here's the formal definition of our limit in multivariables. So formal definition. So the first thing that we're going to assume is that our f of xy, let's say, is defined near our point P that we want to approach. So near P equals, let's say, AB. Okay? Alright, so then we have that the limit, so the limit as our xy point, as xy approaches P, as the point on our xy plane, as that gets closer and closer to P, or anything around P of f of xy is equal to L. Okay? So this limit equals L if for any, and this symbol is called epsilon. It's just a symbol. You could just use another variable. They just like to throw in like Greek letters and symbols and things. So for any epsilon less than 0, there exists, and this will make sense in the end. I'll explain everything. So there exists some, I believe that's called sigma, but I'm not sure, or something like that, greater than 0, such that the following is true. That our absolute value of f of xy minus L, so the distance between the value of our function and the limit it's approaching, is less than epsilon for all xy in, this means in, this one is not the epsilon, which is really confusing actually. So I'll just say for all xy in, there we go, D, which is a disk, and I'll explain all of this. Sorry it's so long, but the formal definition is quite lengthy. But anyway, so that is it. Basically what it's saying is that for any, so let me graph this real quick first. So let's say we have our surface here, okay? So here's point P, all right? So this is the point that we want to approach, right? From any direction or path or anything like that. So what does this disk part mean? We'll start with that. So disk means, the D signifies a disk, centered at P, so this is the center, and this sigma, or that Greek letter thing, signifies the radius. It's a very tiny radius, okay? So this is a small radius here, okay? So that radius is the funny Greek symbol, okay? Anyways, so then epsilon, that just means a really tiny value, right? So if we evaluate the actual value at point P, so this is our f of xy at P, then that means that our L, our limit, our approximated limit there, so this is L, it has to be very close from all of these directions to our actual value, or our L, okay? So anyways, it's just saying, like, from any direction you have to be approaching or tending toward the same value for z, or for f of xy, the value of our function. Okay? So that's pretty much it. So again, I'll just explain this in a less formal way, so more conceptually. So what this says, again, I'll write the formal definition part here. So f of xy minus L, so the difference between our function and the limit, is less than epsilon for all, and then we have x comma y in the disk centered at P with radius this thing. Okay, so what this means is that the difference between the function, the actual function, the value of the function, and the limit itself at that point is small, and this is for all points in or within the tiny disk. Again, this is very small. We're talking about when you get really close to the point P, around point P. Around point P. So, yeah, that's basically it. It's just saying that the limit gets very, very, very close to the value of the actual function, the actual value of the function at point P for all of the points surrounding our point P. So, again, let's say we had, like, point P was here or something. So here's point P, and this is the disk surrounding it with radius of this Greek letter symbol thing here. Okay? So anyways, for all of those points in here, then the value of the limit at each of those must be, or the difference between the limit and the actual value of the function at each of those points in here must be very small and insignificant, basically, for the actual limit to exist. Okay? So anyways, done with the formality of the definition of the limit in multivariables, and now we'll go on to something a little bit more tangible and practical. We'll go on to the limit laws. Okay? So here are the limit laws. We'll present them in succession. So the first one we're going to go over is the sum law. So we're going to be adding some stuff. Some stuff. Anyways, no pun intended. Limit as xy approaches P of, let's say, f of xy plus g of xy. This is going to be equal to, and you guys might guess already, limit as xy goes to P of f of xy separately added to limit as xy approaches P of g of xy. Okay, so that basically means you can break stuff up with an addition sign there. Okay, so the next law I want to go over is the constant multiple law. Constant multiple law. Okay, and this one, we've seen all of these, hopefully, before in like single variable calculus or something like that. So anyways, if we have the limit as xy approaches P of some k, this is a constant, times our function, we can basically just take that k out entirely and just evaluate the function itself of just f of xy, and then afterward multiply it times that k on the outside. Okay, that constant there. Alright, okay, so the last two I'll put on the next slide because they kind of go together. So the third one is going to be the product law. So product meaning the result of multiplying something. So product law, this one's going to be for limits, again. This is part of our limits law. Limit as xy goes to P of f of xy times g of xy is the same thing as if you were to take the limits of each one of those functions separately as xy goes to P. So here's the first one, And here's the second one, limit as xy goes to p of g of xy. And then you were to multiply both of those quantities together. Okay? And the last one is going to be the opposite of product, which would be the quotient law. Okay? And this one's going to be about division, or dividing, right? So we're going to have, if you have the limit as xy goes to p of, I'll put the f1 on top, so f of xy over g of xy, this is going to be equal to the division, or the quotient of the two divided, one on top of the other, but first calculated separately, right? So divided by limit as xy goes to p of g of xy, and this one has a little special condition that if limit of the bottom, so if this entire thing on the bottom, so that would be the limit as xy goes to p of g of xy is not equal to 0. Because if it were equal to 0, that would make this whole quotient undefined, which we don't want. Okay, so that's it for the limit laws. Now we'll move on to some continuity. And in this sense, so continuity, it has the same meaning basically, but now we'll kind of like redefine it in the multivariable sense. Okay, so continuity in multivariables. So what does that mean? So a function is continuous, we'll say. So continuous at, and we'll use our same p point, which is a, b, if the limit of that function as xy goes to p, which is the same thing as ab, the point ab, of our function is equal to the value of the function evaluated at p. Okay? So another way to phrase that is just limit as xy goes to p of f of xy is equal to f, that's an equal sign, equal to f of p. That's the same thing, right? So this is the all-important equation here. Or this one, which is the alternative one. Okay? So now we have, let's say, there's another like offshoot of this, which is the composite. That means like something is composed of something else or made of something else. So so composite of continuous, and I'll abbreviate, continuous functions is continuous. Okay, so basically if you stick one continuous function, so if we have some like f of xy is continuous at ab, this point ab, and g of u is continuous at f of ab, then we have that then g of f of xy is continuous, and more importantly, at AB, at the point AB. So basically, if we have this inside function, right, if f of xy is continuous at AB, then we have the inside is continuous. And then, furthermore, if we had that the outside function, our big G here, is continuous at f of AB, then the entire thing. So then our G of f of xy is entirely continuous. Okay, at that point. All right, so let's do an example.
A country boy drinking beat the odds, watching out for laws on the falling stars. I pray you make it out of the booby traps and feeble death that people give you on the low.